The conclusion from our earlier analysis on the amortized or average running time for the constant increment strategy for array resizing is that in the worst case time and also in the average case time, they are both linear, big O of n. So now we want to see, by applying the same rigorous mathematical analysis, are we able to show that the doubling resizing strategy may have a different running time, average running time more specifically, asymptotically. That's something we would like to do, right? And also remember from the last part, I also derived the sum of the geometric series. In that case, we can also apply the formula if it's impracticable. We'll see. Okay. Let's now switch to iPad over here. And the assumption is you have already studied this piece of code over here about how the resizing strategy works for doubling. Right? That's something I assume. Of course, I will highlight them whenever I need to, but make sure you actually study that. Make sure you actually understand how it works. Alrighty, so let's now talk about the doubling strategy. And again, let me remind you about what's really amortized analysis, right? So when we say amortized analysis, it really means about average, right? So the average, to calculate it, we simply want to calculate what's the total running time. And in this case, we're going to formulate the series of the resizing steps, the different occurrences for the resizing as a series, and try to do the sum of the series. In the early analysis for the fixed increment strategy, the series is simply an arithmetic sequence, but we're not too sure yet about the doubling strategy. We'll see. Maybe it's a geometric sequence series. So the total running time divided by the number of operations. And we have the same assumption as before. So we got n pushes. So we are really comparing apple with apple, right? So for both analysis of the constant increments versus doubling, we are both considering n pushes. So the basis is really the same. We want to see over the n push operations, the average running time, how do they compare? Is one drastically lower than the other or not? And the last push also triggers the last resizing routine, just the same assumption over here, right? But we're going to see exactly how we visualize it. I'll get to this diagram in just a moment, okay? But let me just, again, to emphasize over here. So this part over here is about the resizing, right? You can see this part over here is really, you know what? I think it would be better if I just, first of all, this is where the resizing will actually occur, right? So this part over here, the resizing. And the worst case running time is simply big O of n. It's simply just linear. That's one thing to always remember. The worst case, no question about it, is simply just linear, right? That's the worst case. And we know that this part over here is actually constant, as we said before. This part over here is really constant. And that one there, which we discussed before when we talk about this, the fixed size array implementation for the cube or stack, right? So this part over here is simply big O of 1 over here, right? That one's pretty efficient over here. It's mainly this part that's going to dominate the running time. This part over here, right? This part over here that's going to dominate the running time. This is really the part that's really linear. And the doubling strategy will work by initially our capacity will still be just I. And then every time we need to resize, whenever the size has reached the current capacity, we have to create a new array of capacity multiplied, well, the current capacity multiplied by 2, right? The current capacity could be I, can be 2I, can be 4I, and etc. And then we're going to run this loop to really copy over from all the old contents into the new array. Right? That's really the step, right? So that's about what I need to highlight in the code. Let's now see exactly how the array is going to be resized, right? We still got different resizing steps and we got some math to do. Let's see. Let's say after we created the initial array, it's simply going to contain I elements in the array over here, right? So we got I free slots for us to really do I pushes. You can think of it, right? And what about the first resizing? The first resizing occurs if the first I elements or the first I slots of the array actually got filled out by the first I pushes. In which case, what we got is we're going to get over here, the first I slots actually got filled out, right? In that case, what should we do? what we should do is, number one, we're going to create a new array of size, the current size multiplied by 2, right? I times 2 is going to be 2i, so that's why I put 2i over here. And this loop over here is actually going to copy over all the first I elements, so that's actually what those are what makes the current queue actually full, right? In that case, the current stack or queue, and we're going to copy over all the contents into here, right? So what's going to happen is, for the first I, we're going to copy, and for the next I, they are free. All right. So how much work is really needed to do such copy, right? For the first one, for the first resizing is going to be I. Right? Hopefully you're following. What about the second resizing? For the second resizing, is going to occur if this entire array becomes full. It becomes entirely occupied. In that case, we have to create a new array over here. But now notice how the size is going to grow. Right? It's going to be the current capacity multiplied by 2. The current capacity over here is 2i. Multiplied by 2 would be 4i. So that means we got 4i for the new array over here. That's a very different strategy than just the fixed or constant increments as we discussed before. You can definitely compare the two diagrams side by side, right? So what we're going to do is we're going to create a new array over here of size 2i times 2, 2i times 2. And then we're going to copy over all the 2i elements into here. And then the other 2i will just be free, right? Think about these. These will be the first 2i. These will be the first 2i elements you have to copy over, and this part over here will be free, right? So the copy will actually take 2 times I, right? You can definitely actually move on. It's the diagram is slightly harder to draw for this doubling strategy. Hopefully you can you're okay for now. So let me ask you very quickly. What about a third resizing? For the third resizing, what's going to happen is this part here is actually going to be full. So that means we're actually going to create an array that's double the size of 4i. So it's going to be 8i, right? It's going to be 8i. So 4i is going to be copied over to the new array, and the other 4i will be free, right? Without drawing the diagram, hopefully you can imagine that. Let's now talk about the last resizing. What's really going to happen, right? The last resizing basically is going to happen after n pushes, right? And we assume that this will trigger the last resizing routine, meaning that in the previous resizing, think about what's the second last resizing. In the second last resizing, we must have already created n slots in the array. In that case, we have filled it out. So that's why we got the last resizing over here. In that case, what we're going to do is we're going to actually create an array over here of size 2n. And then the first n over here is actually going to actually copy from the array that's actually resulted from the second last resizing. Right, so that means over here we're going to get this part over here that's going to be copied over, and this part over here is actually going to be free. All right, I'm kind of omitting some details from the diagram, but based on my verbal remarks, you can feel free to draw additional diagram if you need it. Right, but I think I covered all the fundamental steps already. So this part over here is actually going to be exactly n over here, right? And this part here is also going to be n. Let me say it again. This will be the last resizing, which will involve, number one, creating an array that's going to be double of the original size. The original size will be n because we're assuming that we got n pushes, and the last push actually trigger the last resizing routine. So after n pushes, we actually got exactly n items we have filled in. So now we need to do the last resizing, in which case it's going to double the size over here. And then we're going to copy over all the old contents from the original array of size n. So that's why it will take n work to really do the copy, right? Hopefully so far so clear, I really hope, right? So that's going to be n over here. And if you can already see, we actually got a geometric sequence over here with the initial term over here, I, starting with I, and the common factor is actually 2, because every time we want to create a new array and do the copy, the capacity will just be multiplied by 2, right? So if you go to the third resizing is going to be actually 2 times 2 times I, which would be 4i, right? Let's now write it down exactly, right? It's really important for you to convince yourself how this diagram actually help you visualize, and also how to really formulate each resizing diagram over here into the corresponding work, right? That's going to dominate. Let's now try to put down the running time, right? Total running time. You can think about the total running time, right? It's going to be equal to the first resizing is going to be I, the second resizing is going to be 2 times I, and the third resizing, I can also put it here, is going to be 2 times this particular one, right? It's going to be 2 to the power of 2, right? 2 to the power of 2 times I, plus all the way to the final one is going to be n, as we said before. But we want to know, now we know the first term, we know the final term, and also in order to really apply the formula for the geometric sequence, I'm going to apply that over here. We want to know how many turns there are as well, right? We want to know exactly how many turns. Let me just put down the formula over here. Okay, let me just recall ourselves, right? That's the formula we did earlier, right? You can see SK, right? Let me put it here. So the sum of geometric sequence, right, is going to be, the SK is exactly equal to, right here would be R minus 1, and also initial term times R to the K minus 1, right? I just want to make sure I didn't write it wrong. And the K over here is about number of turns over here. It's really important to see that, right? The K over here is really about the number of turns. Number of turns. Right? So that's something we need to figure out. Exactly, right? We know the initial term, and also we need a constant, we know the factor, which will be 2, right? Every time we actually want to go to the new array, we want to double the size, right? That's why the R over here is simply just 2, which is awesome, right? And then we're going to see exactly how many turns there are, right? Let's now do similar pattern observation as we did earlier. This is actually the first resizing, right? First resizing. And let me rewrite it a little bit to help you identify the pattern over here. This one here is simply I multiplied by 2 to the power of 0. All right? And the second resizing is 2 to the power of 1 multiplied by I, right? So this will be the second resizing. And this one over here will be 2 to the power 2. That's the third resizing, right? And I can try to write this a little bit consistent with other form. Okay, so I can say 2 to the power of 0 multiplied by I. I think that'll be better, right? And now we want to see this should be how many turns? Let's say k turn, right? Kth turn over here, kth turn. And what should that be? Over here, according to the pattern we have observed, right? You can see for the first term is actually 0. It's the exponent. The second term, the exponent is actually 1. The third term, the exponent is actually 2, right? Kth term, the exponent should be k minus 1, right? That's really the pattern you want to observe. So that should be 2 to the power of k minus 1 multiplied by I. Agree? Alrighty. And what exactly is k? Now we want to solve it, right? So in order to solve it, let's now try to do it. So let me put the star over here. Let's put it here, right? So I'm going to solve the k in the star over here, right? So we know that 2 to the power of k minus 1 multiplied by I is actually equal to n over here, right? 2 to the power of k minus 1 is equal to n divided by I, right? And what will be k minus 1? So we know that k minus 1 over here should be log of base 2, right? For base 2, I'm not going to write it down explicitly. So it should be log of n minus I and then plus 1, right? So let me actually try to write it slightly in a white space. Otherwise, you cannot really see it, right? So over here, right? That'll be. Let me put it here. Okay. So that means k minus 1 is equal to log n divided by I. So k is equal to log of n divided by I plus 1, right? That's a very important calculation you should know how to do, right? If you have any trouble calculating this term specifically, please reach out to me, right? I'm kind of assuming that you know how to do the basic log manipulation, especially if you say 2 to the power of something is actually equal to this, right? That something should be equal to log of this, right? That's a very basic property of the log. Let me write it down over here, just in case you want to review maybe your earlier math notes. So if I actually say if I say 2 to the power of x is actually equal to maybe y, that actually implies x is equal to log base 2 y, right? So this is a very important formula for you to property for you to recall. For example, 2 to the power of 3 is actually equal to 8. That implies 3 is equal to the log base 2, 8, right? Just in case that helps, right? Alrighty, let's now move on. So now we know how many turns there are. So that'll be the number of turns. And also we know the initial turn, also we know the final turn as well. Okay? Let's now apply the formula for the sum of the geometric sequence. It will be, let's now try to do that. And r minus 1 will be trivial because r in our case is simply just 2, right? So 2 minus 1. And then initial term is simply just I, right? Multiply by. And then we actually got r, which is 2, to the power of k. And k is this particular number over here, right? Let's write it down. And I just need to make myself a little more space over here. There we go. Okay, that should be enough. And 2 to the power of k, which will be the number of turns over here. So that'll be k is log n divided by I, and then plus 1. Plus 1. All right, and then we're going to say minus 1, right? You can see the minus 1 over here. Right, so this is the formula over here. And how do we simplify that, right? There is another log property I would like to show to you, right? Very quickly. Actually, that's not even log, about exponent property. If I got 2 to the power of, well, actually any number. Let's say x to the power of y plus z. It should be equal to x to the power of y multiplied by x to the power of z, right? I'm pretty sure you know about this property over here. And we can apply that over here in just a moment, right? You can think about this one here. 2 to the power of this plus this is going to be equal to 2 to the power of this multiplied by 2 to the power of 1, which is simply just 2, right? So what I want to do here is I want to simplify just this part over here. So 2 to the power of log ni over here, right? What would this be? Right? That's another property we can actually look at over here. It's very similar to this one over here. I'm going to write a property over here. So you can think about that's property number 1. This is property number 2. What about property number 3 over here, right? If I actually got 2 to the power of log x, right? That one is simply just equal to x, right? When I actually got this one over here, I'm really asking about 2 to the power of something will be equal to x. And I'm not saying that 2 to the power of something, I really want to calculate that. In that case, it would just be x, right? I'm sure you actually know about the basic property, right? If you got any trouble, I can also try to help you with that. Right? Just one little example. 2 to the power of log 8, right? Which will be 2 to the power of log 8 would be 3, which is just going to get 8, right? You can see here, it's really the 8 here, and also 8 over here. Just little example. So we know that. So this part over here is 2 to the power of log n divided by I. It will just be n divided by I. N divided by I. Right? And then the plus 1 as the exponent over here would just be equivalent to multiplied by 2, right? Let's now try to simplify once more, right? 2 minus 1 will just be 1, so we don't need to worry about it anymore. So it will be I multiplied by, over here, n divided by I, over here, plus 1 over here is going to become multiplied by 2, right? 2 to the power of 1. And then minus 1. And if you try to simplify just a little bit further, it's going to be n I cancel out, and also 2 times n minus, and also I, right? 2 times n minus I. And we really are seeing something that's very exciting, because this is simply just bigger of n. If you try to compare what we got earlier, right? I would like to maybe use a lighter green just to let it stand out. Okay, it's bigger of n over here, right? You can see this bigger of n is actually the total running time we are calculating. Do you remember what the total running time is for the fixed increment strategy? Let's take a look. That one was bigger of n squared, right? That's a total time. One is n squared. The other one is substantially lower. That one was linear. So now if you try to do the average case or amortized running time, how should we do it? So now we're going to say the amortized average running time, I'm going to put in the sticker over here, bigger of total running time is n, as we just calculated, divided by n pushes over here. That's going to be n. That one would be amazingly bigger of 1. So this is really the conclusion you want to really draw to yourself, right? So let me highlight it over here. So the amortized running time for the push, as we analyze, is actually constant, right? And its average case time remains to be, the worst case remains to be linear. So these are the two comparisons you really want to make, right? So let me just fix this quickly. So they'll be equal over here, right? Let me just highlight once more. Worst case, same as before, just linear. However, if we try to average out the running time for the over the number of pushes, which will be n in this case, because we know that every time we're going to double the size of the array. So that really makes sure the number of resizing operation will actually occur asymptotically less frequently, right? That's really the insight you want to really draw, okay? And then we actually got this, right?